Star Trek. Captain Kirk, Spock, and a few red shirts land on a distant planet. A lone, mysterious creature lurks in the shadows. The red shirts get nervous. Kirk pulls out his communicator and says, "Beam me up." Isn't the communicator an awesome device? The concept of the Star Trek communicator was first revealed in 1964, and now, 50 years later, over 60% of people own smartphones, a device far more capable than the communicator ever dreamed to be, unless you count teleportation. Now, think back to those sci-fi movies you've watched where there are paper-thin touchscreens, transparent displays, or even flexible phones that wrap around your wrist. Haven't you ever wondered if we would ever see this type of technology in our lifetimes? When will we see ultra-long-lasting batteries that can be charged in minutes, or flexible transparent touchscreens? Is that even possible? In 2010, the Nobel Prize for Physics was awarded for the discovery of a multifunctional nanomaterial called graphene. This promised to lead the next generation of nanotechnology. Graphene is a nanomaterial made of carbon. It is a 2D film and the thinnest material in the world, with thickness the size of a single carbon atom. My research focuses on making large, porous 3D sponges out of 2D graphene for fuel cell electrodes, sensors, tissue engineering, and also just because I think it's cool. Despite graphene being the thinnest material in the world, it is also the world's strongest flexible material and is 4,000 times more conductive than copper. It can also survive harsh conditions like you would see in batteries or fuel cells. If that wasn't cool enough, graphene can also be doped with other elements to tune its properties. Doping is like Lego blocks, except we use atoms of other elements to replace the carbon atom and enhance the graphene sheet. Because of all these traits, this transparent 2D conductor was an inspiration towards the idea of flexible transparent smartphones and advanced batteries. So why hasn't graphene left the lab and entered our home yet? One major reason is that researchers, academic journals, and companies sacrifice quality for quantity. The hype of graphene led to a gold rush, where these parties flooded the market with over 3,000 papers in a span of 6 years. That's almost 2 new papers for every day. An overwhelming number of these papers used graphene oxides or flakes of graphene powder, which were passed off as graphene. Now, graphene is a fickle material. It must be made of a single extended sheet of carbon in order to have its core properties. If the sheets get stacked, like paper in a printer, it becomes more like the graphite in your pencils. Kind of boring. If you lay 2 papers side by side, the edges make it tricky to get a perfect continuous sheet. Graphene acts the same way. Its electrical mechanical properties become worse when more flakes are added, which is how graphene oxide materials are made. Because of the dominance of these graphene imposters in research, graphene has been misrepresented as performing poorly in application where it should otherwise excel. Researchers here at UC Irvine work on making the purest graphene possible. We do this through a process called chemical vapor deposition, where metals and gases are sent to 1,000 degrees Celsius, or about 4 times as hot as your average kitchen oven. At these temperatures, the metal becomes energetic enough to separate the atoms in hydrocarbon gases like CH4. Hydrogen atoms are kicked off, and the remaining carbon atoms sprinkle onto the hot metal like raindrops on the ground, and then begin to self-assemble into a graphene sheet. This bottom-up manufacturing gives us the purest graphene possible. After removing the nickel template, we're left with freestanding 3D sponges made up of 2D graphene films. Due to our high-quality processing, our 3D graphene mechanical strength is about 4 times as strong as other graphene foams and 1,000 times as strong as graphene oxide foams. Yet, with this great improvement, our sponges are still 150,000 times weaker than graphene's max theoretical strength. Even with our careful attempts to make the purest graphene possible, we still end up with polycrystalline graphene, papers stacked side by side with their edges fused together, which makes the structure weaker and not as electrically conductive as true single-layer graphene. In the image to your right, you can actually see the edges of these graphene flakes if you look close enough. The image to your left shows a large, wide view of our structure's morphology. Although we don't have single layers, our multi-layer graphene structures are still thin enough to be transparent, allowing us to see the preserved, curved shapes of our 3D structures. We're getting closer and closer to achieving single layers in 3D structures. So, we have some work to do in order to get the ideal 3D graphene structure that can power your advanced batteries and vehicles. These will serve as our base material, which we can experiment with and tailor into powerful devices. We're not quite at Star Trek levels yet, but we're certainly seeing the beginning of something magical. So one day, in the not-too-distant future, we can indeed say, Scotty, fire up the graphene and beam me up. Thank you.